Hello and welcome everyone. This is the first part of the series on thin film flow modeling and simulation within the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements at Luleå University of Technology. The outline of this video is to first introduce you to a model of a thrust bearing where we couple some physics, and then an overview over what I will call a reversed recipe, and then we will reverse that to the original recipe, which will start off with analytical solution of the corresponding linearized simplified problem, and then successively more and more complexity is added in numerical finite difference method based solutions in Cartesian coordinates and then in polar coordinates, and then we obtain a linear finite element model which we can implement in, for example, COMSOL multiphysics. And when we have validated this one, we can carry on and solve the nonlinear problem of the nonlinear, more realistic problem of the thrust bearing that we were interested in studying. A thrust bearing can be found in various applications. It could be found in propeller shaft arrangements in ships. It could be found in hydropower plants where it supports the shaft, the turbine and the generator, which are huge loads, and the dimension of these bearings are extreme. We realized to model this one, we really need to couple a few different physics to have a thrustworthy and valid prediction. And here I have listed probably two of the most important ones, and that is the linear elasticity equations to be solved for the deformations in the shaft, in the collar on the shaft and on the bearing pads. And then we have the most crucial bit, it's the thin film flow physics, which models the thin film, how the thin film flows between the collar and the bearing segments or pads. So some examples here on different pads. We have a very coarse finite element mesh. We have a deformation of that, and we see the pressure distribution that causes this deformation, and the pressure distribution, of course, is also induced by the hydrodynamics of this type of bearing. So if we have this model, we realize it's non-linear, very difficult to verify and validate. So it's really important that we take our time and try to do our best on this, because otherwise we can never have a simulation model which can predict anything realistic in such a bearing. In order to solve this very complex nonlinear model for the thrust bearing in a commercial software, and to be able to ascertain the validity of the solution, I will here present the reversed recipe to do so. So it will anchor the solution of the full nonlinear problem to an analytical solution which we can definitely ascertain as is correct, not only qualitatively but quantitatively. So solving the full nonlinear problem in a commercial software, that's what we do, what we want to achieve. Now, to do so in a rigorous manner, we had to linearize this model. And if we now view the model as we did before, we have the linear elasticity equations that models the deflection, the formation in the segments and the color, and this is now causing a fluid structure interaction also, and non-linearities due to this. And if we exclude this, we can actually have a linearized model, which we can be quite a lot more certain that it would produce the quantitatively correct result. But to really assure that, we solve the same problem in a finite difference with a finite difference scheme in polar coordinates, because this was a rotating device and it lends itself to polar coordinates, and then we can solve this very rigorously with finite difference method, and we have full control over discretization errors and everything. But could be done with an in-house open FEM code also. But okay, I suggest, and what we will do in this course is actually to learn about the finite difference method, and we will apply it in polar coordinates to carry out this comparison. Hopefully we can conclude that they agree well, and then we're happy to some extent. The only thing we need now to ascertain is that the quantities are predicted at right levels. I mean, if they compare well, we have at least got the qualitative agreement. Now, if we adjust the domain aspect ratio so that it resembles a rectangular bearing, then we can later on compare this to a perfectly rectangular bearing in Cartesian coordinate, and that will be the next step. Now, to do this, we can of course increase the inner radius and decrease the pad segment angle, so that the pad itself can be viewed as a rectangular bearing, and the velocity will not vary that much over the small radial difference, since the inner radius is much larger than the outer radius. So it resembles something with a one-directional motion and rectangular geometry. We solve the same problem again with finite difference method, now in Cartesian coordinates. We can compare this to the polar coordinate case with a modified aspect ratio, and hopefully we have a qualitative agreement here again. So what's next? We adjust the solution domain aspect ratio again, so that this Cartesian problem actually represent almost nearly infinitely wide bearing. And why do we do that? Yes, because then we can actually solve a 1D problem instead for 2D flow, and this one is possible to solve analytically, and then we can compare with 2, and we can see that if they not only agree qualitatively but also quantitatively, then we have validated our numerical solution procedure, which we set out to do. We have a validated model. Now, this was the reversed version of the recipe. Let's have a look at the recipe itself. So we start from 1, and in the end we end up at 7. Okay, solving the Reynolds equation analytically. This is possible if we have a problem where the lubricant, the fluid, can be assumed to be isoviscous, have constant viscosity, and have also constant densities. The fluid is incompressible with constant density. Then we have the following very much simplified Reynolds equation, second order differential equation, in terms of the pressure being the dependent variable. So P is the dependent variable, X is independent variable, H is input function parameter, so it models the geometry or the film thickness of this bearing. Eta naught is the fluid dynamic viscosity, and U naught is the velocity, the sliding velocity of the color. And you can think of this problem now as we have flipped the real thrust bearing upside down. So the color sits beneath and the pad is the inclined surface here, the top surface here. In a real thrust bearing, in a hydropower plant, these two change place and the color is on top of the pads. Okay, we have a length of this domain, it's L. So with that we have all the different input parameters except for the boundary pressures, which we here will assume are the same. It's a ambient, the PA, the little a in PA stands for, if you like, ambient, or if you like, atmospheric pressure. So pressure at x equals 0, the left boundary is PA, and it equals the pressure at the right boundary, also PL. Now in this case, with a wedge type of bearing like this, it's very simply modeled as a linear function in x, and that angle in reality had to be very, very small. So alpha makes it possible to approximate the film thickness for not including the tangent of alpha, but alpha itself. And if we do that approximation, we can also formulate it as we have done on the rightmost part of the equation for h of x here, as a linear function in x, which only have two parameters, k and l, and k is a representative of the inclination. Doing so means that we can just integrate this equation twice and obtain the analytical solution. So now we really can ascertain that we have the quantity levels assured, so we will know what the pressure would be for an exact situation of this bearing where we define L, U and eta naught and K and actually also the film thickness, the minimum film thickness at the trailing edge H naught. Then we will know exactly the magnitude of the pressure, and we will also know the whole pressure distribution for this infinitely wide bearing, which means that we can then compare to stage 2, where we instead solve this problem in Cartesian coordinates with finite difference method, and we can implement that for a general aspect ratio of the domain, and we assume here that the motion will be in the x direction, the linear motion of the color will be in the x direction, positive x direction. When we have this solution, we're not so happy at first, because we need to specify it with a very high y to x aspect ratio in order for it to resemble the infinitely wide bearing solution. And here you can see an example with a 10:1 aspect ratio, so wide bearing. And in color here you see the pressure distribution in dimensionless form. So and I've denoted this by P2D, and then using also the aspect ratio 10:1, and it's a function of both x and y, but we can see that it's very constant on a large part counting from the middle and to both sides in the y directions. It's only at the edges things happens, it changes, the pressure changes, and it's of course because of the boundary conditions. It needs to satisfy the boundary conditions there, which we have posed to be atmospheric pressure. So comparing now these two at the exact center line, so where y is equal to 0, we can clearly see that there is nearly no difference visual at all between the two pressures, the one that we obtain for the infinitely wide bearing P1D infinity of xj, and the pressure distribution at the center line for the 2D finite difference method solution. They can be obtained in a very similar, they can be obtained, and when they are compared they are very similar. Look at the quantitative comparison here also. So we have qualitative comparison and we have quantitative comparison, and we know exactly the value of that one. Now the error between them, so now the analytical solution, it's for real. So it's that one we are really certain of, and we can compare, or when we do any comparison of this type to that solution, it is an error. It's a relative error measure also, because we normalize with the sum of the pressures, the sum of all the pressure, which is actually a force balance. So it has a physical interpretation. Okay, so we see that in this case we can get very close to 0, so that the average difference in this sense, the average difference in this relative sense is order 10 to power minus 3, or perhaps 2 if it's closing up to 2. So it's less than 1%, and we're probably very happy. Having done that comparison for the high aspect ratio y to x, we can of course also do the 1:1 aspect ratio, and here we demonstrate that for the real pressure distributions in dimension, and also you can see x and y here are in dimensions. So assuming that the ambient pressure is 0, we get a net pressure, maximum pressure increase of about 850 850 pascals for this bearing, and this is because it's a very small bearing. It's only 4 by 4 centimeter, and we lubricate it with air. Eta node is 1.5 E minus 5, which is a typical number for air, and air viscosity, and the sliding speed is just 1 meter per second. We have a minimum film thickness of 1 micrometer. So for the color to ride on a 1 micrometer film, in this case, we must generate this pressure distribution within that bearing. What we can see clearly is the pressure varies in both directions, similarly in both directions, because of the aspect ratio and the closeness to the boundaries in both directions. And this solution has been obtained with 64 by 64 number of elements, so 65 grid nodes in total, meaning that we have solved actually a 63 by 63 matrix linearized system in terms of matrix times P equal right hand side vector. Having the rectangular solution, or the solution for the rectangular problem, we now move to the polar coordinate model, and if we solve that for similar configuration, we end up with this solution, and it is in many ways very similar to the one that we saw before, except for that the variation of the velocity from the inner to the outer radius causes a small skewing of the pressure distribution, but otherwise it's pretty much the same. Now, keeping this 1-to-1 aspect ratio, I have put these quotation marks here because it's not, I mean, of course it's not 1-to-1, but it's nearly, it's not so way off even at this scale. But if we then increase the inner radius, maintain the same aspect ratio as before, we have this problem, and you can see now we have of course changed things to maintain the pressure, and what we have changed is the velocity actually, because in this case the radius is much larger, so we have to change the rotational the angular velocity to lower it to have the same velocity over the entraining edge, well, over the whole bearing, dragging the fluid in over the segment. And we do that again, we increase the inner radius, and we also now turn down the angular velocity a little bit more. We get this, and this is the actual code for it. Well, but here we also have a picture where we have increased the inner radius further, and now we see that we have a more or less rectangular bearing, and we realize that from 0.4 to 0.44 there will not be a tremendous change in the velocity, the velocity in the y direction over that segment. It will be more or less linear in the y direction, and we have obtained that by, as I said, changing the angular velocity omega here in proportions to the mean radius, which increases all the time here as we increase the inner radius. Otherwise, things are the same as before, and this is what it looks like if we view the solution on the center line. And what do we mean by center line? On the mean average line. And we can see that for the higher or for the large pad that we had in the beginning, which is the least rectangular, there is a slight difference visible here, but it's quite small, and we could actually be quite confident that we have solved this problem correctly. But if we now increase the inner radius more and more, we can clearly see that these two start to overlap, meaning that we have obtained a valid solution also in the polar coordinate case. So we have it. We have now we have the possibility of solving the thrust bearing, the flow in the thrust bearing by means of the finite difference method in polar coordinates, and this is an example solution of what it looks like. And because of this, we can now use a commercial software, for example COMSOL Multiphysics, to solve the problem within a finite element type of discretization. And when we have done that and compared and ensured that we have now a connection all the way down to the analytical solution, then we can continue to add non-linearities, and we do this very carefully by making parametric studies to ensure that that adding these non-linearities really reflects how the physics behaves in reality. And that was it for the intro of the course.